Hello, today I want to talk about blind source separation in biomedical signals using variational method. And I'm Yasaman Torabi, PhD candidate from McMaster University. And my supervisors are Professor Sharon Shani and Professor James Park Riley. And this presentation was presented at the 14th Southern Ontario Numerical Analysis Day 1-day annual conference, or the SONAD 2025. And what I basically want to talk about today is, first of all, the motivation, why it is important to use the variational method, and what is exactly a variational autoencoder. Why not reuse a standard autoencoder? And then I talk a little bit about its architecture and how we kind of regularize its latent space, what is its loss function, and some of the tricks that we need to use when we are using the variational autoencoders. And then I talk about its application in the biomedical sound separation, the thing that I'm using in my research, and a visualization of its latent space. And finally, I talk about the advantages and disadvantages of using VAE, its limitations, and what are our next steps in our future works. And in the end, I summarize the stuff and give you the references I used. So basically, blind source separation is a problem of recovering source signals from mixtures with limited or no information about the sources and the mixing procedure. So, for example, in my case, we want to separate heart and lung sound because they often overlap when we are listening to them in auscultation, and it's really difficult to separate them manually. So we are trying to find ways to use generative models like the variational autoencoder to separate the sources. Okay, so if this is our encoder, X is our input, and here it is our output, and this is the latent space that we have. So what is a VAE architecture? So basically we have an encoder and a decoder and a latent space, just as a typical autoencoder. But this encoder in here is learning the mean and variance of a normal Gaussian distribution. And then we sample from that normal distribution, and that parameter is going to be our Z for the latent space. And it is kind of giving a kind of regularization term for us. So in here, instead of just focusing on the difference between the input and output, we want to kind of regularize the normal distribution function in here that we have. We try to have them in a way that I'm going to talk about them later, that the cubic library difference between the normal Gaussian and the standard normal Gaussian is the minimum. So how they can do it? So the whole idea of the variational autoencoder is in this regularization term that's added into latent space based on the cubic library diverges. If you see this picture on the top, there are some points in the latent space that they are meaningless when they are decoded because they are from empty space parts in a typical autoencoder. And if 2 points are close, the outputs in the decoder are not necessarily similar. One of them is a triangle, one of them is a square. So we don't have continuity and we don't have completeness, meaning that if we choose 2 close points in the latent space, the content may be completely different. And there are some points that the output in the decoder are totally meaningless. But this cubic library divergence that we add, because of that generative feature that it adds, it causes a fully distributed latent space, so we ensure that nothing is meaningless And if 2 points are close to each other, the outputs are similar. And the latent vector, they try to be pushed toward the unit Gaussian in the center. X is in our case that we want to use the autoencoder for separation. X is gonna be our observed mixed signal, and ZA is our prior latent space. We get then Q is gonna be the neural network related to the encoder, and its weights are shown with phi, and theta and P are related to the decoder. So in the encoder I give X and I get Z. In the decoder it is vice versa. In here I want to make sure that the likelihood of getting something similar to the X, something similar to the input from my decoder is as much as possible so that reconstruction error is minimized. And at the same time, this P of Z is set to a standard normal prior. And at the same time, I ensure that all those neural networks that I had related to the encoder probabilistic model that get my input and generates my Z in the latent space is as close as possible to a normal distribution. So it wants to regularize the latent space so that ensure that the latent space is fully covered, but they are not kind of overlapping too much. And then when I generate the mu's or the sigmas, I want to get the z's by sampling from that. But when I use this method that I have the mu and the sigma and I make a normal Gaussian thing and sample from them, there is not gonna be a way to kind of do backpropagation in the neural network to train a model. But if we apply a reparameterization trick, then we can enable the gradient descent. So this part is only used when we want to write a code, and mathematically they are equivalent. So I make a sample from a normal, a standard distribution function, multiplied by mu sigma and add mu. Mathematically they are the same, but in this way the whole model is going to be differentiable and I can use the gradient descent. So in our case, in the biomedical sound separation, our input is going to be mixed time frequency features from the heart and lung sound. And in the output, we have the latent representation of the meaning pool clusters of the sounds. And in the decoder, we have different components for the heart and the lung separately. So for example, in here it is the SCFD and the sound representation of a sample mixture. And here are the visualization of the TSNEs. TSNE is basically a method, as you may know, for showing high dimensional things in a lower dimensional thing. So as you can see in the early phase of training, the latent space is unstructured with a lot of overlapping features. One of them is related to heart, one of them is related to lung sound. Each dot is related to one sound. And in the mid-training phase, during the training, the clusters are initially begin to kind of be generated. So initial clusters begin as the model is starting to differentiate the patterns. And in the final stages, in the late training phase, as you can see, we have distinct cluster forms that indicate that the source separation was successfully done. So what are the advantages of using VAE? The most important thing is that it's fully unsupervised and it doesn't need any label sources, and it learns the latent space interpretably. And because it has a kind of generative feature, it's very robust to noises and variability, so that if there are some kind of small noises, it is ignore them. And this image is also one more representation of what's happening inside a variational autoencoder. But what are some limitations when we are using the VAEs? The VAEs are real sensitive to latent dimensionality and the weight that we use for regularization term, and it has a lot of complexity and computational cost. Most generally, when we are working with the latent space, the dimensions should be very high so that it can fully learn the whole features of our sources, because everything is unsupervised and it doesn't have any label to learn. So the model is going to be so complex most of the time. So in future works, we potentially we want to improve the model complexity and find some potential improvement by finding ways to decrease the complexity and find some better regularization terms in the loss function. So to summarize, VAE is an encoder based on variational inference method, and the statistical analysis is typically working based on the Bayesian rule, and it has a feature that helps it to regularize the latent space to generate some new data. And as our research is progressing, we anticipate the enhancement of blind source separation technique in this research field. And here are some of the references that I used during this presentation, and thank you very much. If you have any question or you want to do any collaboration, feel free to drop me a line, and here is my social media and my email that you can contact me. Thank you very much.